Now this morning, we have an opportunity to explore one of the cornerstones of physics. That is quantum mechanics. And our guide is Dr. Stephen Girvin. Now, Dr. Girvin is a professor of physics and applied physics, and is interested in quantum mechanics, particularly in the development of quantum computers. Along with his colleagues in engineering, Drs. Deveray and Sholkoff, they've fabricated an artificial atom using the same fabrication techniques that are used for integrated circuits, the processes that are inside of your computers. And using these methods, what they'll learn, they'll be able to connect the physics of our world to the physics of the microworld. So we're really in for a great treat. So with that, please sit back and help me welcome Dr. Girvin to the podium.
Okay, we'll see if the classical computer works here. Okay, good morning. So I'm going to tell you a little bit about a very interesting and very famous physicist, Richard Feynman, and about quantum mechanics, which is a subject that is near and dear to the hearts of all physicists. And Richard Feynman quantum mechanics is a very rich theory. There are many different ways you can look at it. And Richard Feynman invented a particular way of describing how tiny particles like atoms and electrons and particles of light called photons move around. And they move in ways which make no sense whatsoever. I'm going to be telling you things that sound completely crazy and completely incorrect. And it was extremely difficult for the people who invented quantum mechanics to believe that these really crazy things were happening. And it was just such a strange turn of events to understand that reality doesn't work the way we think it works. And of course, nowadays that quantum mechanics is 75 or 80 years old and we've gotten used to it, there are still surprises. And the fact that you could perhaps someday build a computer that behaves quantum mechanically is an idea that's only about 15 years old and was quite a surprise when people realized that it was true. Things are so strange, you might, if you're interested in what I talk about today, it really follows from this little book by Richard Feynman, QED, Quantum Electrodynamics, The Strange Theory of Light and Matter. Things are so strange that in the early days, people like Niels Bohr, who helped invent the subject of quantum mechanics, if someone came with a new idea, he would say, well, that's crazy, but it may not be crazy enough to explain what's going on. You can also look at I'm going to have some demonstrations at the end, and there are some photos of those and some background material that are visible on my web page. So before I start, I might just tell the kids here a little bit about my own background, because it's a little unusual. I grew up in a tiny village in northern New York State in the Adirondack Mountains. There were 5 kids in my high school class. We had no library. The math teacher taught business arithmetic. That was as high as it went. Didn't have a physics teacher. But with good luck and some help from some of my teachers and my parents, I didn't have enough money to go to college, but I was able to get a scholarship and was able to fulfill my dream and become a physicist. So I encourage you to think past the donuts and what's on television this afternoon, and think ahead to what you're going to do with your lives, and think about the possibilities of becoming a scientist, becoming a teacher, becoming a musician, whatever it is that you want to do. And I hope you are able to fulfill your dream as I have. Okay, so Mr. Feynman. So Richard Feynman was a very interesting guy. There are a lot of, when you go to physics graduate school, you learn all kinds of stories about him. Some of them are even true. And he certainly did nothing to discourage lots of stories about himself. And he's been described as no ordinary genius. A sort of ordinary genius is somebody who is so smart, they do this brilliant new thing, and you say to yourself, well, if only I had been 10 times smarter, maybe I could have done that. But Feynman was somebody who just seemed to come up with new ideas and results magically. And you say to yourself, I have no idea how he did that, and no matter how smart I am, I could never do that. And he liked to play a lot of practical jokes, and when he worked on the Manhattan Project during World War II at Los Alamos, where the atomic bomb was built, he used to like to break into safes and leave notes for the security people saying, you should really lock up these secrets more carefully. He also, while he was there, invented, they had to do a lot of computing. And in those days, they didn't have computers. Well, the word computers meant a person who used a mechanical adding machine to do calculations. And he was in charge of a large team of Army privates with these Marchand calculators, mechanical calculators. And he invented new ways of speeding up calculations that are very practical and are used in your PC today, so-called vector processing. He also is sort of the godfather of nanoscience, or one of the godfathers. He got interested in the idea in the 1950s about how small you could make things. Could you make a transistor that just was made of a few atoms? Or could you build a really tiny, tiny electrical motor? And he offered a prize of several $1,000s to somebody, the first person who could make a motor, electrical motor, that was smaller than a 64th of an inch on a side, figuring he would never have to pay off. And about a year later, this guy, William McClellan, presented him with this little electrical motor. You can see the wires coming out here, and that's the head of a pin. So I don't know how this person machined that little motor, but they looked at it under a microscope, and they could see it turning around, so Feynman had to pay him the $1,000. Okay, so on to quantum mechanics. So, well, first, before we understand quantum mechanics, we have to understand what mechanics is. So mechanics is the study of how things move. It's not necessarily the study of how you repair cars. And how things move. Well, planets move in orbits around the sun. If you're an auto mechanic, you want to see how well your car accelerates. If you play baseball, you want to understand the trajectory of the pop fly going into left field. And in the last 300 years, starting with Galileo and Newton, physicists have come to understand that there are laws that can allow you to predict, if you know the initial velocity and direction of the baseball, you can calculate how it's going to go up, and gravity is going to pull it down, and you can calculate the path that it's going to take. And it was understood, and everything seemed fine until the beginning of the last century, around 1900. Everything seemed fine. Physicists seemed to understand everything. But then people realized that things were made of very tiny particles, atoms, and then they discovered the electron, and then they discovered particles of light, that light was not a wave, but made of particles called photons. And they found out that all the laws of physics that we thought were so perfect are actually only approximations which work for large objects like baseballs, but fail completely for tiny objects. And the thing that's going on with my experimental colleagues who are trying to build a quantum computer here in this building upstairs on the 4th floor, they're trying to make relatively large objects, objects that contain around 100 billion atoms, which is still so tiny you have to look at it under a microscope, but it's much larger than one atom. They're trying to make those rather large objects behave quantum mechanically, and it's very, very difficult, but they're making a lot of progress. So what happens with the laws of physics is that it turns out you cannot say, if you throw a baseball and it's nice and massive, you can say, look, it was here, then it was there, then it was there, then it was there, it moved on this trajectory, and I can predict ahead of time, if you tell me how fast it's going, where it's going to go. But these things, for tiny objects, the location of the particle becomes kind of fuzzy and uncertain. And the trajectory that it takes becomes unknowable. And if you look and see which trajectory it took, you can actually change the situation. So one of the strange things in quantum mechanics is that when you look at something, when you learn information about it, you make a measurement on it, it changes. So here's classical mechanics. Here's my friend Jay Ingram lying on this bed of nails here. And I have this very large sledgehammer, which I just used to smash a cement block on his stomach. And then my friend here is holding up a piece of plexiglass to protect Jay's face so it'll look good at the funeral. And there's absolutely no uncertainty here. You know that Jay is going to die. Well, he didn't really die, but you know exactly with this large object like this sledgehammer, if you took a picture of it and measured how fast it was going, you could predict exactly where it's going to be a little while from now. But it does not work that way in quantum mechanics. Things are rather different. So in the classical world, we say that the fact that you can predict what's going to happen to the positions of the particles later, given where they are now and how fast they're going, that's called deterministic evolution. That's a big word. It just means that you can predict the motion of the particles. Well, it's kind of like that in the quantum world, but unfortunately, certain things that you're sure you should be able to know, you're not allowed to know. It's a very strange circumstance. Certain things that you would like to measure become unknowable, or they seem to become random. Each time you do the experiment, you may get a different result, even though you prepared. If you take an electron and shoot it on a path like a baseball, and you always aim it in exactly the same direction, and you always shoot it with exactly the same speed, it doesn't always land in the same place. It chooses a place somehow randomly. Well, when people began to develop a theory of this quantum mechanics, they realized that what was happening was that these very, very tiny particles seemed to be acting like waves. If you've seen a wave on the Long Island Sound or on a lake, it's this kind of big object, and it's oscillating up and down, and you can't say exactly where it is. It's not at one point. It's some kind of large, fuzzy object. And it seemed like particles were acting like waves some of the time. And the inventor of this picture of quantum mechanics, Erwin Schrödinger, thought about the electron as a wave. And when you have a wave, this somehow represents where the particle is, but you can't say exactly where it is. Somehow it's more likely to be where the wave is big and less likely to be where the wave is small, but you can't say exactly where it is. Feynman took a different point of view. He said, no, particles are particles. Electrons are definitely particles, but they take paths which you can't predict, which are random, and then they even can take more than one path at the same time, which sounds, that's the first of the things that sounds completely crazy, but is in fact correct. And these two ways of describing quantum mechanics seem completely different, but in fact make the same predictions and are consistent with each other. But they were just invented by different people looking at the physics from a different point of view. So I want to convince you now that light is made of particles. So we have lights up here coming down, shining on your eyes. There's light from this screen shining in your eyes. But there are so many billion of these tiny little particles per second hitting your eyes that you don't notice the individual ones, although your eye is almost sensitive enough to detect the individual ones. So the way we can, physicists figured out that light is made of particles is they took a light bulb, and an ordinary light bulb emits energy in the form of light, and it is in the form of these particles called photons, and there are about 10 to the 18 of these per second. What does 10 to the 18 mean? It means 1, the number 1, followed by 18 zeros. Okay? It's a, what is that? That's a trillion per second of these particles. So each particle doesn't carry very much energy, but there are lots and lots of them, and it's coming out of a 5-watt light bulb. So we want to get rid of most of them, so we put a dark gray piece of glass here called a neutral density filter, and it absorbs almost all of those particles of light. But about 1 per second maybe goes through this dark thing and comes out the other side. And then there's a gadget called a photomultiplier, which when it receives this little lump of energy, this particle called the photon, it detects it, turns it into a burst of electrical current, and you can use that to drive a loudspeaker, and you can hear it click, or you can see a needle move, and you can detect the presence of these particles. So if you do this experiment, you'll hear about 1 click per second, but it's not click, click, click. It's not 1 click every second like a clock. Sometimes you get click, 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 click. It's random. Sometimes they're too close together. Sometimes there's a long space. You cannot predict when photons are going to arrive. It seems to be random. It's like the Amtrak trains. You can never tell when they're going to come to New Haven, even if there's a schedule. So this proves that these are not waves, because waves deliver their energy smoothly and continuously all the time, even if they have very low amplitude. But here, it's showing that the energy arrives in discrete lumps called quanta. It's from the German word for counting, for quantity. And that little lump of energy always has the same size and makes the loudspeaker click when the photomultiplier detects it. So that's the first bit of randomness. So instead of a photomultiplier, there's another related way to detect photons, and many of you may actually own such a thing. In your digital, if you have a digital camera, inside there is an array of several million little detectors, each of which is capable of detecting single photons. So here's a special, this is a $30,000 digital camera, but it's more or less the same thing. And we expose it to a very, very dim source of light. And after 1/30th of a second, you saw a photon landed right there and made a little dark spot on the image. This is a kind of negative image. And one landed there, and one landed there, just at random. And then after 1 second, you see 30 times as many as that, roughly. There are probably roughly 90 spots there. And you're beginning to detect a little bit of a pattern. They're more likely to land here and here and here than in the spaces in between. And after 100 seconds, so a little over a minute and a half, now you can really see that there's a pattern. There's lots of photon particles landing here and here, but not very many in between. And we're going to come back in a little while and explain why it's making this pattern. But what I want you to learn from this is that light really is made of particles. And if you tried to take a picture of your friend and you opened the shutter for such a short length of time, and the room was kind of dark, so that only 3 photons landed on the film or on the digital camera detector, you just get 3 randomly located spots. The one time when you do it, they might be here. The next time you do it, they might be here, here, and here. It's completely random, and you have no way of predicting it. Even if you set up the experiment the same way over and over and over again, the results are random, and there's no way to find any, there's not any hidden things that you forgot to take into account that are explaining why it looks random. It really is random. On the other hand, things are kind of predictable, because after you do this, once you have about 10,000 photons landing, then you see a very clear pattern. And those kind of patterns can turn into a picture of your friend's cat or whatever it is you've taken a picture of. But when you first have just a few particles of light landing, it's not a full picture. It's just random. Well, let's try to understand that. And let's start with so what do physicists do? So that's a very strange phenomenon. Let's say we just discovered it. How do we work as scientists? How do we figure out what to do? Well, we make a model. A model is the beginnings of a theory. A theory is sort of the highest form of, a theory is an explanation. It's the best and highest form. At first, we're going to start with a rough model, just an idea. Maybe it works like this, and we're going to try out the model and compare the predictions of the model to experiment and see what we get. So let's start with a simple model called geometric optics. It's a very nice thing. It says, okay, light's made of particles. I'll believe you. And let's just, what do particles do? Well, they probably travel in straight lines. Let's try that as a picture of what happens. So here's a little source of light. And here's a little arrow I cut out of paper and I put here. And it casts a shadow. You've all seen, you can see shadows from the overhead lights if you hold your hand out on the floor, you can see shadows of the seats here. So it's very simple to explain shadows. This model works great. You put the object there, the particles of light go, and if they hit the object, they get stopped. And so they don't land on the screen, and so they make this dark area called the shadow. And that works if you have a source of light, and well, I don't even need that. I've got one up there. There's my shadow, And it's because I'm intercepting the particles of light and keeping them from hitting the screen that makes this shadow. Okay? So this model, this simple model that light's made of particles and travels in a straight line, seems to work. It's great. Maybe we've found a way to predict how light travels. So we could try a different shaped object, and sure enough, we would get a different shaped shadow, and it would make sense. Everything would fit with the model. Well, there's a problem with this model, because you can do another experiment that shows that the model is no good. So this model of geometric optics worked great for several hundred years, and people were very happy with it. And then, actually, Isaac Newton was the first who sort of invented that model, also realized it had a very serious problem. And the serious problem is that there's a thing called partial reflection. If you have a piece of glass, like a window, and particles of light come up to the window, some of the particles of light go through the window, and some of them reflect. You can see that at night. If you look outside where it's dark, there's no light coming from outside, but if there's a brightly lit room that you're standing in, you can see a faint reflection of yourself in the window. It's kind of acting a little bit like a mirror. Even though it lets light through, it also reflects light a little bit. It turns out that with an ordinary piece of glass, 96% of the light particles will go through the glass, and about 4% will reflect on average. Okay? And a particular place where this phenomenon of partial reflection is used is in your car rearview mirror. So some of you don't look like you're old enough to drive yet, but maybe you've seen your parents at night reach up and do something to the rearview mirror in the car to adjust it for nighttime use. Well, the way that works is the following. The idea is you want to reduce the reflection of the light from that mirror, because the headlights of the cars behind you will blind you while you're trying to drive. So car rearview mirrors are made of glass, and it's not a flat piece of glass, it's a wedge that has a taper like this. And on the back side is some shiny aluminum that makes it a mirror that reflects almost all the light. So in the daytime, you set it up so that the light coming from the cars behind you bounces off the back surface and goes to your eyes so you can see. But at night, that's too much, the headlights make too much glare. And so you tip the angle of this thing so that the light that's coming to your eye is the one that's bouncing off the front of this wedge, the front surface of the glass. That's only about 4% of the light. Well, what's the problem? Well, here's the problem. If light's made of particles, and I sent to a piece of glass, if I sent one particle of light, is it going to reflect or is it going to transmit? It can only do one or the other. If you put a detector or a photomultiplier behind and it transmits, it will click. If it reflects and you have a detector back here, that one will click. But they'll never both click. It can't go both places at the same time. So what does it mean that 96% of the particles transmit and 4% reflect? It means that there's some randomness, that if you send in 100 particles of light, typically 4 of them will reflect and 96 will transmit. But which ones? You cannot know. You cannot predict ahead of time. When you do the experiment, I'm going to send in one particle of light and I'm going to measure whether it transmitted or reflected. The result is random. 96% of the time it will transmit, but 4% of the time it will reflect. And you can't tell what's going to happen until you do the experiment. Then you do the experiment over again with exactly the same setup, launch exactly the same light energy, and sometimes the result will be different. You can't predict. So Newton actually was aware that this was a problem for his particle theory of light, but he didn't know how to get around it, and quantum mechanics didn't come along to explain it for another couple of hundred years. Well, there's some more strange things, experiments you can do, which show that this model of geometric optics is no good. And this brings us to, maybe you've heard of this Heisenberg uncertainty principle that people talk about a lot but understand less, usually when they're talking about it. So it turns out that if you measure the position of a particle very, very accurately so you know where it is, you cannot tell after that which way it's moving. That when you make a measurement, you actually change the system. So in the geometric optics, if I had a nice beam of particles of light coming like this, and I put a little tiny hole in a screen, then what will happen? Well, these guys will all be stopped, casting a big shadow here. And the particles that are exactly lined up to go through that tiny hole will go straight through, and they'll all land right there. So you do the experiment. You have to make this hole very tiny, about 1/millionth of a meter in diameter. A meter is about this big. 1/100th of a meter is about that big. A millimeter you can just see with your eye, and this is 1,000 times smaller than a millimeter. But once you make it that small, you find out that instead of going straight, after you've determined that the position of the particles is exactly here, because they had to be there to go through the hole, they come out in random directions. Sometimes when you send one particle in, it comes out up here and lands on the screen there. Sometimes when you send it through, it comes out down here and lands on the screen there. You cannot predict where the particles are going to land. And that's this uncertainty principle. If you're very, very certain about the position, the height where the particle went through the screen, which you are because it went through the hole, you're now very uncertain about which direction it's heading afterwards. That's called the phenomenon of diffraction and cannot be explained by geometric optics. So this position and the direction are called incompatible observables. If you know one, you can't know the other. Well, now we come to the really, really strange part of quantum mechanics. Suppose that I put that one slit there and I got that distribution of where the particles land. Now let me open a second slit, so I should get twice as many particles going through, and the light should get brighter. Well, in some places, the particles never land. And in other places, they land more frequently. So imagine if you had two flashlights and you turned on them both, it would get twice as bright, right? So whenever you open a second source of light, you expect to get more intensity, more particles landing everywhere. But instead, you get 4 times as likely that they'll land here, and they won't land here at all. That's very, very strange. So opening a second slit actually causes the light intensity to decrease in certain places. Something that just sounds crazy, doesn't make any sense at all. So somehow it turns out that if you send in a single particle of light and it comes here and it might have gone through this slit or it might have gone through that slit, it has a choice of 2 possibilities, then something strange happens to the probabilities of where it can land. Sometimes it can't go to certain places. And that's the experiment that I showed you with that digital camera. There were 2 slits, and the particles are arriving randomly and landing at different places, but they have a higher probability of landing in certain places like this, and almost no probability of landing in the intervening spaces. Opening the second slit made the light intensity here go down. Very, very strange. So this is Feynman liked to call quantum weirdness. A particle takes, so he said, let's make up a crazy rule to explain this crazy experimental result. Let's say that each particle of light takes all possible paths from the light bulb to the detector. It's not like a baseball. You launch it and it goes along the same path every time you do the experiment. Here, every time you do the experiment, the particle doesn't choose one path randomly. It takes both paths at the same time. Well, that's very strange. And basically it means we cannot know which path the particle took, because that would affect the result. Well, that's a pretty strange idea. On the other hand, the results of the experiment are pretty strange, so let's see if it works. So there's a second rule, and the rule that Feynman made up to see if it would fit the experiment was that each particle carries a kind of stopwatch, a little clock with a second hand that turns around very, very fast. Well, it turns around 10 to the 15 times per second. We won't worry about that, how fast that is. Let's just say it's keeping time. Okay, so each particle carries a clock that runs at some rate which is determined by the color or the frequency of the light. And here's the really strange rule. It says you should pretend the particle took this path, see how long it took by what time the clock says when it gets to the detector, and then pretend that it took this path also and see what time that clock reads when it hits the detector. Maybe this path is longer than that path, so the clock readings are not the same because it takes longer to reach the screen. And then there's a rule for combining these clock readings to calculate the probability that the particle actually landed there. And that rule is the following. You take the little arrow that represents the second hand on the clock from the first path, and the second one, and you add them together like vectors. For those of you that know what those are, you just put the tail of one on the head of the other. And then you draw a line from the beginning of the first one to the end of the second one, and then you make that into a square. And the area of that square, when it's big, that tells you there's a big chance that the particle will have taken those paths and landed at that place. And when it's small, then there's not much probability that that will happen. So the area of the square determines the likelihood that the particle will arrive at this particular random destination. And so sometimes when the particles take the same length of time, or the arrows on the second hands are parallel, then the length from there to there is very big, and you get a big square. Sometimes the arrows are lined like this, and when you go from the beginning of one to the end of the other, you get a very tiny square. This is called interference. This is called constructive interference. This is called destructive interference. And it means that if the arrows line up like this, you have a high probability of going to that place. If they line up like this, you have almost no chance of going to that place. So you get this very strange result that sometimes when you have two different ways to go to the same place, so you would think it would get easier to go there, you can't get there. How weird is that? So that's what's going on here. When you look at paths here that are symmetric, that is that you go here and here and then there, and the length of the path is the same, then the clock readings will be the same because it takes the same length of time. The first path arrow and the second path arrow will be parallel. You'll get a big square, and therefore lots of probability of landing there. And then for other places, they'll be out of phase like this. You'll get a small probability. And then as you go further, they'll be parallel again, and you'll get a big probability. And that explains this so-called two-slit interference pattern, where you get lots of probability here and none there when you open the second path. Now you say, well, that's crazy. How can it take both paths at the same time? I can just find out which path it took. I will put a little detector here, and when the particle goes by, my detector will click, and I'll say, oh, well, it took path 1. Well, you can do that experiment, and when you do it, it destroys that interference pattern. The act of finding out, becoming certain which path it took, ruins the interference effect, because it turns out, when you study quantum mechanics carefully, that when you measure that it went through here, that measurement act randomly resets the position of the second hand on the clock and destroys that nice interference pattern. So which path it took is unknowable. You can't know it, no matter how hard you try. And if you try and measure, you change the results of the experiment. Very, very bizarre. Well, what happens if you have many, many slits? I showed you first one slit, then you got something funny with two slits. Maybe you get something very strange with many, many slits. And here is an example, and you can do some of these demonstrations. I brought some with me. You're welcome to come up afterwards and do some. You find out that you can take a compact disc like this, any favorite music disc except Bach, because that's classical. It turns out that these compact discs have many, many, many slits in them, kind of, and they like this. And it turns out that the angle that the light reflects from that shiny mirrored surface isn't like an ordinary mirror where you come in at one angle and you go out at the same angle. Now, the angle that it comes out depends on the color of the light. And if you take one of these compact fluorescent light bulbs and look at it through this, by reflecting it off this compact disc, you will see all these funny different colored lines. And that's also quantum mechanics in action, because inside this light bulb over here is a mixture of gases, and the atoms inside that gas have their electrons get excited by the electricity in there, and they jump up to different quantum mechanical orbits that the electrons can take inside the atom. And then when they fall down, they emit light of different colors, different energies. And you can see those individual quantum mechanical events by just looking at this light through this funny grating. You can also, just to show you, illustrate this effect. So here's the CD, and I can take this laser pointer, and so on an ordinary mirror, the light would just go down and bounce up at one angle. But if you look closely here, you can see many, many different reflections of the light. If I hold things still, you see there's a spot near the bottom of the picture, one further up, and there's one up on the ceiling. And there's another one on the ceiling, and another one. I better not go any further. So the light doesn't just bounce off at one angle. It bounces off at several different angles. And if you send in one particle of light, which would be too dim for us to see, it would choose one of those angles randomly. Sometimes it would go here, sometimes there, sometimes there. Very strange. Okay. So I guess the message is that when it comes to quantum mechanics, you have to think differently. So I'll be happy to show you some demonstrations afterwards, including one with a dusty mirror that's kind of fun. Thank you very much.